You're listening to Let's Talk AI.
Okay, welcome to Let's Talk AI. This is our podcast today. Our guest is Rodney Smith. Rodney is an assistant professor of chemistry in the Faculty of Science here at the University of Waterloo. So, Rodney, thanks for joining us today.
Happy to be here. Thanks for the invite.
Well, so to get started, let's go right back and start at your background. Where did you do your studies before UW, and then how did you get an interest in AI?
I had kind of a long, convoluted path to get here. So I started at the University of Manitoba back in 2002 in the bachelor's program there. And so I studied initially primarily organic chemistry during my undergraduate degree. After that, I decided I wanted to get out of Manitoba and go kind of expand my global perspective. And at the same time, I wanted to avoid paying international student fees. And so I stayed in Canada and went as far as I could, which brought me to Newfoundland. And so I went to St. John's to attend Memorial University of Newfoundland for my PhD, where I switched focus into more surface science and catalysis and electrochemistry, electrocatalysis. After that, I jumped over to Calgary for my first postdoc. And so I started studying more inorganic solid state materials there, developing new compositions and again, sticking primarily to electrocatalysis. I went afterwards to the University of British Columbia for another postdoctoral position where I also kind of spent a bit of time into a startup company that we were doing to commercialize some of the catalysts that I had developed during my research. Finally, I got some international money, so I got funding through the Alexander von Humboldt program in Germany to go work in Berlin for a year. And so I moved over to Berlin and worked at one of their synchrotrons for a period of a year. And then I transferred over to the University of Waterloo and started my position here.
Excellent, excellent. So now you're using AI to do your research. Where did the AI thing start? Where did that kind of overlap into your path?
It really started fairly recently, and so within the last 2 years or so, basically what was happening is we were becoming overloaded with data, and so the way that I like to approach things, we're studying things on kind of the atomic or molecular level, and when we start looking at solid state materials on this level, there's a lot of uncertainty, and so we're limited basically in characterization techniques that we can apply, and every characterization technique has a combination of strengths and weaknesses. And so we try to overcome the weaknesses of individual techniques by combining multiple together. And so we might do multiple types of spectroscopy to, for example, watch electrons move around and watch bonds vibrate and measure bond distances and things like that. Then we take all of that information and we try to correlate it together. And so, we were very quickly coming to this situation where we would put everything in a Microsoft Excel spreadsheet and try to look for relationships across data sets, and it becomes very, very tedious and frustrating. And so this brought us into some of these open source machine learning packages. And when we start using some of those, it really dramatically simplified life. And so now what we're trying to do, we've used a lot of it in a more of an interpretive sense and data processing and digesting information. And what we're trying to do now is build up some experimental information so we can move more into the predictive realm.
Okay, so you used the word catalysis when you were talking about your path. Let's back up for a second and explain the why behind this. Why do we need catalysis? What's the purpose?
It all comes down to speed. And so if we're thinking about the synthesis of chemicals that we use in daily life, or if we want to move towards sustainable fuels, things of that nature, we're looking at chemical reactions. And so in order to uh, basically satisfy the international need, the volume of chemicals that we need to use for any of these purposes, we need to produce it on a very large scale. The easiest way to do this is to make reactions go faster. And so if we have a slow reaction, we have to build a huge plant, a big industrial plant that's going to cost a fortune in initial investments. If we can increase the rate per unit area that we start driving these reactions, what we can do is get by with smaller plants, right? More efficient processes. And so this is where catalysts come in, is basically what they do is help reactions move faster.
So you talked about sustainable energy. Can you kind of give us a little more insight or a deeper dive into how you're using the catalysis, the AI for sustainable energy?
So what we have primarily focused on in my group are energy-related reactions, and so things like water oxidation and water reduction. And so basically, we're taking that H2O molecule and trying to split it into hydrogen gas and oxygen gas. Of course, the hydrogen gas is then something that we could use for other chemical processes for synthesis, or we could start using it directly as a fuel, as we see big pushes in parts of Asia and Europe. And so the AI aspect of this comes really into the optimization of the catalysts. And so when we make these solid state catalysts, they're messy things. And so there's a lot of, we often picture solids as being kind of static, robust. They're a rock, they just sit there. In reality, there's quite a lot of dynamic changes that occur on the surfaces and within the structures of these types of materials, especially when we start doing reactions on them. And so when we start doing that, how we study this is again in a range of spectroscopies and crystallography and a lot of kind of X-ray based techniques, let's say. All of these generate parameters, numeric parameters, and some information. And so the AI aspect, from our perspective, what we've been doing, the AI aspect has been used to process and study a lot of those parameters. And so if we generate information about the surface and the bulk structure of these solid state materials, and study them while we're doing reactions actively, we can watch what's happening with all of these different parameters. And again, we get this mountain of data that we get buried under if we don't have tools to really start to navigate it.
You mentioned dynamic materials. I have a little bit of background in these electrodes understanding. So I understand they actually slowly erode away or kind of fade away, and then they have to be changed at a certain time. Do you study those kind of things or predict it? Or because a lot of times they're buried deep in a reactor and they're hard to monitor because they're in the reactor. So
Yes, so getting it into the reactor requires that we have some reasonable understanding of the long-term stability of these things, and so there's a number of different processes that we have to be aware of when catalysts deactivate, and so one is kind of corrosion or erosion. And so if we're corroding, for example, steel, we're oxidizing it over to iron oxide, and then we're kind of starting to dissolve some of those iron ions away, and we're actually losing material from the surface. We can also undergo transitions in structure where one structure might be active for the catalytic reaction, whereas another isn't. And so, again, this is kind of, we can do this either while the cell is operating, or we can operate the cell, take it apart, and look at the materials afterwards to try to deduce what must have happened. And so we do a little bit of a combination of both. And so I think all of that is necessary to understand the stability and the behavior of these materials. And again, this builds that mountain bigger and bigger. And so we have very diverse information coming in on every single material that we study.
so as a society, we're moving towards, electric vehicles and mandates across not just Canada and North America, but globally. Do you see your work affecting the future push for electric vehicles? And are they going to be in every battery in every car? Or, give us some insight there.
Um, so I think we're living in a very interesting time because we are going through this push that we're going to move away from kind of conventional fossil fuels. When I started all of this, there was this concept that renewable energy was never going to work. You go back, don't have to go back very far, late 90s, early 2000s, it was still, solar energy is too expensive, wind energy is too expensive, it's just never going to work. And now we're in an era where it's actually cheap. Right. And so we can generate all this sustainable energy, and we need to do something with it. Right. And so that energy, when we generate it, is electricity. We have to convert that electricity into a form of energy that we can store. And that's where batteries and fuels come in. And so in the battery realm, I think it's quite interesting that we're seeing kind of a global separation right now, where North America primarily is pushing towards batteries and electric vehicles. But if we go to places like Europe and Japan, instead is pushing towards hydrogen and alternative fuels. And so we're in this kind of realm where we have competing technologies, and we'll see exactly how things play out in the long run. What I've primarily studied are the fuel side of things rather than the battery side of things. And so generating hydrogen or trying to turn CO2 into some useful chemical, so it's not just a pollutant basically. And yeah, so I think that we are going that route. The way that my research contributes to all that is really understanding the chemistry of these materials, and so this is a very big complex problem that spans kind of physics, chemistry, all the way through engineering and public policy and politics. And so the politics side is starting to get sorted out. That doesn't necessarily mean that all of the science side and engineering side are getting sorted out as well. And so my research, we're looking at really optimizing the structure, the behavior, and the stability of solid state materials that we could use in things like electrolyzers and fuel cells. And there's that's one aspect. After that, once we have an optimized material, we do still need to consider optimizing the engineering and then the design of, for example, you had indicated batteries, that the design of a new structure for a battery, the design of a new reactor to convert hydrogen, water into hydrogen, for example.
Do you see there's going to be a winning solution, or maybe a hybrid of the two?
Um, I'm teaching a fourth year undergraduate course in chemistry right now, and I kind of introduce this as the Betamax versus VHS sort of situation, right? Are we in a world right now where we have two technologies that are going to kind of fight to the death, and one of them is going to prevail, or are we going to have to adapt? I personally think that neither of them can fully win. I don't think that batteries are never going to go anywhere. They're going to be useful for some things. The question is whether they're used for everything, or whether hydrogen and alternative fuels start taking more of a role. And I think, again, seeing that there is the split in the world, I think what we're going to see is quick advancement of both technologies. And so we're going to see a diverse range of batteries developed. We're going to see a number of alternative fuels and optimization of the materials and engineering surrounding hydrogen generation, for example. And ultimately, I think that we have to come towards kind of a hybrid vehicle that is fuel cell based on hydrogen plus electricity through batteries. And so I think that we're going to see that form of a hybrid supplanting the conventional gasoline hybrid.
A lot of times the new technologies are for aircraft, aerospace, defense, other applications. And then once we've finally figured it all out, then they slowly trickle down to the automotive. Is that the same scenario that's driving your technologies?
Here, I think it's actually reversed. And because of the energy demands of things like airplanes, the whole aerospace industry wants to move towards sustainable fuels, but it's a much more demanding process. And so there's a lot of effort going on there. But we do see, for example, I think Air Canada just finished buying or placing orders for a number of battery operated airplanes. But that's definitely not mainstream yet, whereas we do see mainstream electric vehicles coming out. And so I think that the political environment has kind of set it that we can do this backwards this time. And so we're seeing development at the consumer level. And it probably helps that we have things like our smartphones and our tablets and our computers, that a lot of these technologies have been developed for decades. And so really it's a matter of, again, optimizing those materials to tweak where we apply them to something where we need higher energy, higher power.
So are you part of an association developing this? Like, who's funding all your great efforts?
So my research is funded from a variety of sources. Most of it is tied in with federal funding or provincial funding, and some of it is collaborations with industry. And so much of the fundamental chemistry aspect of it is funded through purely federal funds, and so through Natural Sciences and Engineering Research Council of Canada, for example, the NSERC. I obtain a lot of funding through Canada Foundation for Innovation and other kind of conventional venues in Canada for buying equipment and infrastructure so that we can study these. Once I have all of that in place, we also have a number of projects going on, for example, looking at electrochemical sensors for various species and solutions that could support manufacturing processes, anti-corrosion coatings for manufacturing processes, and things of this nature. And so they're all based on similar concepts where we have solid state materials that we use to basically, we characterize with a range of different techniques, and we generate loads of information that we have to process.
Okay. Do you do collaboration with other local institutes? I know Western, for instance, has Surface Science Institute, and different things like that.
So I am a member of the Waterloo Institute for Nanotechnology and Waterloo AI as well. In terms of specific collaborations that are going on there, nothing really prominent at the moment. It's more so a group of like-minded people coming together to have discussions and share infrastructure that would otherwise be out of reach of each individual person.
So, but outside of Waterloo, are you collaborating with any other universities in the region?
Uh, Not in the region. I do collaborate internationally, and so we have a collaboration that we started a few years ago with the University of Duisburg-Essen, and so there's a number of faculty members over there that I work with, studying kind of two-dimensional materials, these emerging materials that have, if you've heard of graphene, it's kind of like that, but based on metals instead of carbon. And so we've used some of those collaborations, and we've leveraged as a group here those collaborations to generate a large scale collaboration between the two institutes. And so we have, I think it's 9 faculty members from Waterloo and another 9 or 10 from University of Duisburg-Essen, that are coming together to kind of try to take these emerging materials from a laboratory kind of curiosity into a commercial setting. And so we're looking at learning to synthesize them on a larger scale, learning to understand the structure, and whether we can maintain all of those neat properties that we see in a lab on a bulk kind of industrial scale, and then apply it to things like LEDs and batteries and energy storage.
I know there's a big push for, I guess they call it AI for materials discovery, and they have these automated things. I mean, it sounds like you're doing a similar thing, but a little more manual intervention in there, human intervention.
Um, yeah, one of the key issues, I guess, with artificial intelligence is that you need data, right? And so we see it out there in the public very often in the context of media and technology, because we can get a lot of data, right? And so places like Google and Facebook have reams of data that they can use to really develop big models. In the solid state materials situation, we don't have that much real world data, and so for context, somebody like Google, or you look at some of the databases containing images for processing and upgrading and increasing resolution of images, and they're looking in the multi-million to billion data points. In solid state materials, the longest running database that I'm aware of is the International Crystallography Database, which has something around 100,000 unique samples inside of it, right? And so, and this has been going on for 100 years, right? So they've been accumulating this information for a very long time. It's been standardized, and it is actually curated, and so that everything coming in is high quality. And so when you compare those, you can see that we're orders of magnitude off in terms of data volume, right? And so it becomes a bit more tricky to train really high quality predictive models in that sense. The way that people have gone instead is into using computers to calculate and predict structures and to predict properties. When we do that, of course, what we can start doing is growing the volume of data points. And so as the volume increases, then we have maybe a more robust model, but then it depends on how well those values were calculated, right? And so it depends on the assumptions that you made when you started. What I try to do in my research instead is trying to bring more of that manual experimental information into a bigger form, right? And so again, this is a very slow, expensive process because we use expensive infrastructure. We use a lot of manpower and salaries that have to back all of that up, right? But we're making efforts now that I've started doing AI and seeing some of the benefits and strength of it. Within my group, we've kind of created our own internal database. And so what we're doing is directing all of the information that we generate in a standardized format into this internal database with the intent that we can start using this in more of a predictive sense as it grows.
So you talked about your group. Got online and looked at your website. You have what, 6 or 8? How are they all fitting into, and how do you recruit them? And is that growing team? Is that where are you at with your group?
Um, Recruitment is the hardest part of the job. So trying to so we have a diverse range of projects that we take on, and so at the moment I think it's 6 graduate students and 3 postdocs at the moment in the group, and so I think my website's a little bit out of date at the moment. I need to update it, but out of that, about half of the graduate students are about to graduate, and I'm looking at pulling in a whole new cohort of students. And the challenges there really comes down to synchronizing funds, right? And so I often get students that want to work off cycle when I don't have extra money available, and then when I do have extra money available, there's not the students that are around, right? And so I conventionally I try to recruit by visiting other universities. I try to recruit through classes here at the University of Waterloo, through emails to colleagues, and basically anywhere that I can try to get exposure to students. I'm always open. I watch my email and I get all sorts of information sent to me from students interested in applying. And so my door is always open. I'm always looking to recruit people. But yeah, we're looking at expanding. We do have money coming in, and so the group is starting to grow nicely, and everything is starting to scale. So I'm definitely on the lookout for students.
And what would be this ideal candidate? Materials specialist, an AI specialist, a bit of both? What are you looking for?
A little bit of both. I think again, because we have each individual project is or each individual funding program is kind of targeted on a couple of different objectives that are kind of tangential to each other, and so each of those objectives requires distinct skill sets. Very often, I'm finding more and more what I do, kind of a classic chemistry education gives people a good foundation, but when they come in, they don't know the day-to-day stuff, right? And so I don't expect anybody to come in and be an expert or really be all that knowledgeable about machine learning or any code-based information or anything like that, any computer science. We kind of pick up things as we go, and so we've developed internal resources to help people grow into new areas. The key thing for what we do is again, we're very much chemistry focused, and materials, solid state structures, and so a decent understanding of chemistry, chemical engineering. And so I often pull out of our chemistry program. I've had discussions with people in physics, for example, and we have the materials nanoscience program here at Waterloo as well, that kind of spans engineering, physics, and chemistry. And so all of those types of backgrounds give sufficient knowledge to get into what I do.
Excellent. Well, I think we've pretty much given an overview. If you have any final thoughts or comments you'd like to
add? No, I don't think I do.
Awesome. Well, this has been great. At least we have a little better understanding now of who is Rodney Smith and the research and areas you're focused on, and what is catalysis and how is it affecting our future. So thanks again for joining us today on Let's Talk AI.
Thank you very much, Harold.